Today, I, Payal Mahapatra, and my teammate Akash Pandey are going to present a survey that we conducted on transfer reinforcement learning for domains differing in state action spaces. So, reinforcement learning agents suffer from a very popular exploration exploitation dilemma, because of which they need a large number of interactions with the environment to understand the dynamics and arrive at an optimum policy. Using transfer learning, we can actually leverage a lot of external information from a source domain to a target domain which may have a perturbed version of the environment or probably a disabled agent. And that is the whole motivation of trying to do a transfer learning in reinforcement learning agents. Let's look at some more motivations for doing transfer learning in RL agents. On the top left corner, we see a sumo wrestler which has been trained in a self-play fashion and is exposed to a windy environment for the first time, but it is still able to perform better than an agent which has just learned walking. So this shows the efficacy of doing transfer learning in domains which seem to share an inherent latent representation. Transfer learning has been extensively studied in the context of supervised learning. It has gained a lot of popularity and for all the right reasons in reinforcement learning as well. So here, formally put, it aims to learn an optimal policy for the target domain by leveraging exterior information from source domains and interior information from the target domain. Now let us look at some popular transfer learning techniques that are commonly used in reinforcement learning context. The first one is reward shaping. The idea behind reward shaping is to assign higher rewards to more beneficial state action pair. This is also an idea similar to intrinsic reward. One of the common approaches is a potential based reward shaping where you use a similarity function to augment the already existing reward distribution. The second approach is to learn from demonstration, where we assume that there is an expert teacher policy that is already available. LFT methods are usually very specific to the underlying RL algorithm. For example, in a DQN based optimization, we use two different replay buffers, one to store the experience gained by the agent and another to store the experience from the expert. And we use a stochastic policy for sampling so that at every time step, we are also able to sample some of the expert experience. This policy transfer, which assumes availability of multiple expert teacher policies that can be used either adaptively or directly reused to learn a student policy. The most common category of transfer is the representation transfer, especially after the meteoric rise of deep neural networks and how they have found use in deep reinforcement learning as well. So this is something which is directly inspired from the supervised learning setting, and it assumes that there is a disentangled representation where we can have a domain invariant and a domain specific latent representation of the features. And with this transfer, we hope to transfer only the domain invariant features between the source and the target. After the survey, we realized that there are very few works where the action space between both the domains is differing, and there are even fewer work which have attempted to actually use a model fee approach in order to transfer the knowledge between differing state action spaces. We would like to highlight the importance of such a setting. For example, if there is a humanoid robotic agent which is working in probably a factory setting or a manufacturing floor and has probably 100 degrees of freedom and the dimensions for the state action space is quite high, there can always be a scenario where because of hardware malfunctioning or just because of lower specifications, we have another agent which has a lower dimensions of action space. We would effectively want to utilize some of the experience gained by this teacher policy and transfer it to a student policy. And with this motivation, we would like to propose our take on such an algorithm, which will be presented by my teammate Akash in the next few slides.
So, based on whatever my teammate Payal presented, our research interest currently is to transfer the knowledge from between the two domains, which has differing actions or the state and or or the state spaces. Our hypothesis is that if we incentivize the agent for exploring, then agent will go on to explore more, and hence it will gather more information about the environment, which will help us when we transfer this knowledge to the target domain. It will help the target agent to learn faster. That's our hypothesis. Based on whatever we have discussed in the previous slides, this is the proposed architecture with which we are planning to do a transfer learning in future. So the main important thing which we saw in the previous slide is that we want to train our agent in the source model to be more exploratory. So we want it to explore more. There are a lot of models which are available to do that. Already a lot of studies has been done in the literature. There are one type of models are called a forward dynamics prediction model. So there are models based on error based models or the entropy based models. In all these things tries to make the agent explore more. There are also called random network models, which are basically, again, these are for the model free approaches, but this also helps in exploring more, not only optimizing but also exploring more. So whatever our source agent has learned, we want to transfer that to our target domain. Now the target domain transfer happens through two things. One thing is like the domain invariant latent representation, which is directly taken from the source, and the second one is domain specific representation, which is NN1 and NN2 here, in which the weights get updated based on what it wants to learn in the transfer in the target domain. So this is how we are going to do a transfer learning in future. So based on whatever we discussed in the previous slides, we have reviewed the state of art works on the transfer learning in RL. Based on whatever we proposed in the previous slide as an architecture, we want to test that hypothesis which we proposed, and we want to take a teacher which is more efficient than the in the source domain, and in the target domain we want to have an agent which is less efficient, like let's say a robot which does not have one of its arm working, for example. That is what we want to take as a source and the target domain. And once we test our hypothesis, we will report, like we are motivated to report our performance benefits normally using a general metrics. Yeah, and we'll see which if this type of transfer learning is giving us some kind of benefits. Thank you.